afternoon or good morning, everyone. It is good to see you again. We are very happy to be resuming our GLAZE webinars now in 2021. The year had already started in a good foot for everyone, I guess. So again, good to have you back here. For today, we're gonna have one of our own. So Professor Neil Mattson will be presenting the webinar today. Dr. Mattson will be talking about urban CEA, optimizing plant quality, economic and environmental outcomes. So let me start with a brief bio on Professor Neil Mattson, and then we can go to the webinar. So Professor Neil Mattson earned his Ph.D. in 2007 from the University of California, Davis, and he has a master's and bachelor degree from University of Minnesota. Neil joined Cornell University in 2007 and is currently an associated professor and greenhouse extension specialist in the School of Integrative Plant Science. His research is focused on the physiology of both floriculture and vegetable crops in controlled environments. Research interests from Neil include supplemental lighting, strategies to reduce greenhouse energy use, conventional and organic nutrient management, and plant abiotic stress physiology. Mattson is the director of the Cornell Controlled Environment Group, Controlled Environment Agriculture Group, and of course, Neil is also the principal investigator of the GLAZE Consortium at Cornell University. It is definitely my pleasure to be working with Neil for all this time. Neil, thank you so much for being our speaker today. I look forward to your presentation. Just before we start here, I want to tell everyone, if you have questions, please use the Q&A box. You can use the chat as well, but the Q&A is much better for us to keep track afterwards. And I want to let you know that these and all the other GLAZE webinars are recorded and they are available at the GLAZE website, glaze.org. That said, Neil, thank you so much, and you can start.
Thank you so much for the nice introduction, Erico. And it's great to see more than 80 participants today, many of whom are very good friends. So that's always a little bit enjoyable and a little bit intimidating at the same time. Great to see you all. Those of you that haven't seen me in some months, the facial hair thing is new with COVID too. So yeah, life goes on. Okay, so we'll talk about urban CEA. And then the kind of the intro for today is I'm going to give an intro to urban agriculture in general. So before we go into urban CEA, just kind of where does CEA fit into the context of much broader urban agriculture. Then I'm going to talk about an economic study, which is on the environmental and economic footprint of urban CEA. Then we'll delve into nutrition of CEA crops, optimizing CEA, and then workforce development. And I'll mention, I think it'll be a few slides in, I'll mention specifically this, so all of these things connect to a National Science Foundation project, and I'll mention the other team members that are on the project, which are a huge part of all of the research that I'm going to be talking about. So then more broadly, I wanted to point out that urban agriculture takes many forms. Only some of them are controlled environment agriculture, right? So those are things from rooftop farming to community gardens and backyard gardens, and even on people's like porches. Then within CEA, some of them are actually, like rooftop greenhouses, aquaponic systems, hydroponic systems, indoor farming. And then this is from a 2016 publication, but some people also position Peri-Urban agriculture as part of urban agriculture as well. So being in the surrounding areas, maybe within about an hour of a large city. And the different forms that urban agriculture takes, it can be conducted on an individual level. It can be at a community level or business level. It can take form in different locations, so outdoors in gardens, on rooftops, and high tunnels, greenhouses, containers, and plant factories. And then urban agriculture can be both for-profit in the commercial world as well as nonprofit. And here's an example of a really great nonprofit urban agriculture uh, business or group called Harlem Grown. And so they do a lot of projects. They use empty lots in Harlem and work with their local schools and get school kids engaged with doing gardening and learning about fruit and vegetables. So the products of urban agriculture are many, and I think typically when we talk about CEA in urban areas, we're mainly focusing on vegetables, possibly fruit, and especially like leafy greens and herbs as quick turn, kind of higher value perishable crops. But more broadly, urban agriculture is used for cut flowers and edible flowers, mushrooms, fish, chickens and eggs, bees for honey, insects for protein, and other value-added products as well. One example I was thinking of is Renewable is a New York-based company that turns food waste into liquid organic fertilizer. So there can be this whole like nexus surrounding urban agriculture as well that leads to many different types of products. We also see around like New York City, for example, different technology solutions that address CEA or urban agriculture that are part of the kind of nexus of businesses surrounding urban ag. And there are many benefits of urban ag. I think in this slide, I call them potential benefits of urban ag because they're not always realized, but certainly the possibilities are there that they can contribute to economic security and sustainability, the empowerment of small business owners and entrepreneurs, access to employment opportunities and job training, expanded access to nutritious food, community beautification and safety, and then greater opportunities for interpersonal connection. And these bullet points come from work that was done by Anu Rangarajan, who's a close colleague in horticulture at Cornell University. And she has a recent publication you can check out, something like all 220 pages of it, called The Promise of Urban Agriculture. And so it was a national study that she did with Molly Reardon, profiling many different types of urban agriculture. And those opportunities for interpersonal connection, I thought were great. They were highlighting that as one of the things they see that happens more in urban ag as opposed to rural agriculture. So beyond those benefits, there are many challenges of urban agriculture. And these bullet points also come from the same report, The Promise of Urban Agriculture. One of the largest ones, and something that all of the people that this report had profiled, was access to land is very difficult in these urban areas. So the high cost of urban land, the limited possibility to expand a business and increase your production efficiency, and in general, like the higher costs of living and doing business in cities, which could include the labor costs and utility costs, for example. Because of those, it's typically thought that producing a saleable crop in an urban environment is going to cost more than producing that saleable crop using traditional methods in like a field and shipping it into the city. And so the thought is that marketing channels might need to place a premium on local foods to stay competitive, so that those urban agriculture businesses can stay in business. You also, in an urban context, there's not as much of a support system for agricultural production. One of my colleagues that's an economist would call it conglomeration economies. And so we often lack that in an urban environment where we don't have a supply system, a system of trained employees and cohorts and other growers that we can talk to. So those kind of have to be developed from the ground up in urban agriculture. And then in terms of production systems, if one is wanting to grow in soil in the urban environment, one has to think about possible soil contamination, such as from lead, for example, or one has to think also about air pollutants such as ozone that could reduce crop productivity. So in this National Science Foundation project, we wanted to look at what are the capabilities and bottlenecks of controlled environment agriculture in an urban context. And just kind of intuitively, it seems like there could be several things that CEA can help us address that would otherwise be difficult in urban agriculture. One of the foremost being that in at least northern locations, by having a controlled environment, we can produce this local food year round. And then by virtue of being in a space use efficient manner, in a greenhouse or a vertical farm, and with year-round production, we can produce a lot more crop output per area. So if one looks at like greenhouse lettuce production in the US, we often achieve 20 to 25 times higher yields over a year than does a corresponding field. And then many of our CEA systems don't use soil per se, so using hydroponics or soilless substrates. So if there were issues with the soil that one wanted to use in an urban context, we can get around those. The water use efficiency, so we have to compete with households and and businesses for water use, and there has to be enough water for a CEA business to expand. In terms of employment, CEA can offer stable year-round employment rather than seasonal employment. And then some of the processes in CEA lend themselves decently well to automation. So there could be possibilities of addressing some of the input costs in CEA that might be more difficult to address with traditional field-based agriculture. And this was kind of the status quo of urban CEA in New York City as of 2019. In terms of commercial CEA companies, there's many more nonprofits, but in terms of commercial CEA, 7 different companies were identified by Wiley Goodman and Jennifer Minner, who are also Cornellians. And these 7 companies were estimated to provide 151 jobs, which is wonderful. It's funny, it does seem like kind of a drop in the bucket compared to all of the millions of jobs that there would be in New York City, though. And then the types of produce that these operations were producing were the largest number were leafy greens and herbs. And then vine crops were less common, and other kind of niche crops were microgreens, fish or shellfish, edible flowers, and strawberries. So there's, I think, a lot of potential for urban CEA that isn't necessarily being realized currently, but there is a lot of potential. And so with this National Science Foundation project, we wanted to look more at what is the scalability, or what is the potential scalability of CEA in metropolitan areas. So on this project, the first 4 people are from Cornell University. So Miguel Gomez and Chuck Nicholson are economists. Anu Rangarajan is in horticulture with me. She leads Cornell's Small Farms program. And then Marion Neiman at Rensselaer Polytechnic Institute she's a wonderful analytical chemist. So she's based in civil and environmental engineering at RPI. And then she brought with her the capabilities of our team to analyze plant secondary nutritional compounds. So we'll be talking about some of that work in a little bit as well. And the overall framework for this study is we wanted to consider say 5 different metropolitan areas that were scattered around the US, which have interesting different environments, and then look at the possibilities of growing lettuce, tomatoes, and strawberries in those urban areas in either greenhouses, plant factories, or skyscraper farms. And we're still kind of working on the skyscraper farm analysis, so that will end up being a subject for a future talk. And then compare that to status quo production. So often in like the field in California or Arizona or Florida, and shipped to the location is often the status quo. And so we wanted to look at the effects on the environment in terms of water use, energy use, and carbon footprint as well as the possibilities for workforce development as well. And so these were the objectives. So kind of that food systems analysis, looking at the scalability of urban CEA. One of the things that I'll talk about today that really excites me as a plant scientist is optimizing CEA. So if there are bottlenecks such as like energy use, or if we're concerned about crop nutrition, how can we optimize those factors in CEA? And then in terms of the practitioners in urban agriculture, developing peer networks so that they develop their own conglomeration economies or support systems to help each other out. And we really used workforce development as kind of a rallying point for that. So I'll talk about this structured format that we really interviewed many different individuals to learn about workforce needs and tasks, and how that has become a whole different dimension of this project. So the first component of our research I want to talk about, we've been talking about it for a couple years now, but it was finally published in 2020, which is an economic and environmental comparison of conventional and controlled environment agriculture supply chains for leaf lettuce in US cities. And in this case, we looked at New York and Chicago. We looked at greenhouses and plant factories as being the two CEA implementations. And then we looked at the total landed cost of growing the product in greenhouse or plant factory, or in the status quo, which in this case we took as field in California, and shipping 2,000 miles to Chicago or 3,000 miles to New York. And so we do this economic analysis that I'll talk about, as well as looking at environmental indicators in terms of energy, carbon, and water use. So a couple caveats about framing our experiment is that we were looking at some very specific configurations of CEA. We didn't attempt to look at like all different configurations or what are the best business models for CEA. So we assumed it was in a hyper-local situation, which would be in an urban area, very close to the city or in the city. Other definitions of local vary. So I think USDA definition of local is within 400 miles of produced within 400 miles of where it's sold. Other definitions might be more like in-state or within 100 miles. So this was looking at hyperlocal CEA. And again, not assessing what might be the cheapest business model or the best business model, but looking at production in like production of lettuce in an NFT system, in a greenhouse, and in a plant factory. So the system boundary for the analysis, which is something that I think the economists really like to talk about, is that we were looking at what it took in terms of input costs to produce the lettuce and then transport it to wholesale market. We didn't look at the economics after that point. So we didn't look at the price that the producer might get paid, or the effect of moving through the wholesale to retail to customer chain in terms of its effect on like the energy use or carbon footprint. So we looked at production and getting the plants to market. And some of the assumptions that we made are that in a greenhouse, we assumed we had a 1 acre greenhouse that could produce 454,000 kilos per year. So it looks like 100 kilograms per square meter per year, which is certainly achievable in greenhouse CEA. One has to be operating a lettuce greenhouse quite efficiently to achieve that. So you could get lower productivity. And in that same 1 hectare greenhouse, we assumed that you could produce the same amount of heads of lettuce in a 0.08 hectare plant factory. So we assumed it was a plant factory that had 10 layers. But then we assumed that there was aisle space between plant towers. So in the end, like half of the square footage in the production area was allocated to plant towers, and the other half was aisle space. We also assumed that both a greenhouse and a plant factory needed to have kind of like a head house or a packing area and offices that were connected to them. And we assumed that that was the same amount of area, whether you were in a greenhouse or plant factory. And then based on some calculations from the literature, to produce the same amount of kilograms of lettuce, we would need 101 hectares of field in Salinas to achieve that. In our scenario, which is very urban, so in New York, we assumed that we were in the middle of the boroughs, not in Manhattan, but that land is still quite expensive. So land was almost $6 million per hectare. In the Chicago metro area, we looked a little bit outside of downtown Chicago, so a little bit more Peri-Urban, and we assumed that it was about $750,000 per hectare in that scenario. So like I say, it's not trying to demonstrate the best business model for CEA, but if we are growing in CEA in an urban area, what are the realistic costs? And so then in terms of transporting to market, we assumed that our field-based production was in Salinas, California, so 4,800 kilometers to New York, 3,500 to get to Chicago. In the New York City, we assumed that the greenhouse or plant factory would be in Bronx, where land is somewhat more affordable. So that would be 3.5 kilometers to a market, to a wholesale market like Hunts Point. And then in the Chicago scenario, we were assuming we were in Portage, Indiana, which was about 75 kilometers from the Chicago International Produce Market. Okay, so let's see how the costs of production stack up. So we have these 3 bars for New York and then 3 bars for Chicago, which is field production in Salinas and then shipping to New York, greenhouse production in New York and plant factory in New York. And then the same for Chicago, field, greenhouse, or plant factory. Within each of these bars, through this economics exercise, we allocated costs into these different categories. So from the bottom up, those were supplies, labor, packaging. Oh, I need to make sure that you guys can see the same slide as me. There we go. So we have field to New York, greenhouse and plant factory in New York, and then we have field in Chicago, greenhouse in Chicago, and plant factory in Chicago. Then from the bottom up are supplies, labor, packaging, energy, which is in yellow. Then we have structure, which is kind of that bright green, transportation, which is second from the top, and then other. So a couple of the take-home messages here were, by our estimates, the total cost of field production was about $3 per kilogram. It was ever so slightly less for field to Chicago, and that would be accounted for by the slightly lower transportation cost to get to Chicago. And then in a greenhouse or a plant factory, we're looking at $8 per kilogram, whether you're in a greenhouse or a plant factory. And I remember being quite surprised by the analysis that greenhouse actually had a similar production input to plant factory. I was assuming it would be cheaper because of lower energy costs. In the New York City scenario, if you look at what we call structure, that's actually the cost of the structure plus the cost of the land amortized over several years. And so a greenhouse required substantially more land than a plant factory. And in this scenario where land is super expensive, that actually came out to be quite important into the overall cost per kilogram. So while the greenhouse did have about a 2.5 times lower energy cost than a plant factory, it also had about a twice cost for the land and structure as the plant factory. One of the other take-home points is that if you look at greenhouse or plant factory, by far the largest color of the bar is labor. So labor made up half of the production cost. And as I mentioned earlier, we assumed a very unautomated system. We assumed an NFT system where one is manually conducting every step. So from seeding to transplanting to harvesting to packing. We also included overhead for like managerial labor and sales labor as well. So labor was the largest cost. And then depending on if you're in a plant factory, energy was the next highest cost. If you're in a greenhouse, the land and the structure was the second highest cost. In the case of Chicago, the cost for either the plant factory or the greenhouse came out as being a bit less than New York City, and that was largely due to the decreased land costs in the scenario that we looked at. Then in terms of the carbon emissions of production, so this would include like the field production and transportation for the field scenario, or for the greenhouse and the plant factory, it would include the like lighting and HVAC, and then the shorter transportation to market. So, so here we have the calculated kilograms of CO2 emissions per kilogram of lettuce. And for New York City, one of the things to point out is that this was quite close between a greenhouse and field production. And so the transportation costs of going 3,000 miles from California were fairly equal to the cost of heating and lighting a greenhouse in New York City. And then a plant factory had about twice the carbon emissions because all of the light has to come from electrical lighting and greater HVAC costs as well. In the case of Chicago, the greenhouse carbon footprint was actually quite a bit higher than for the field. And that was for a couple reasons. So in Chicago, the field was shorter distance to market versus our CEA scenario where we were outside of the city, where land was cheaper, had a longer transportation cost. So that contributes partially to the reason. The second reason is we, for these calculations, we looked at the mix of electrical energy that was available in New York City versus Chicago. And so New York has more nuclear and renewable energy than Chicago did. And so while the energy usage might have been fairly similar, the carbon emissions were actually greater in Chicago. And then similarly for a plant factory in Chicago, there was also more than twice the carbon emissions as a greenhouse in Chicago. In terms of water use comparison, in our study, we looked at the literature for kind of historical values, and we assumed that both the greenhouse and a plant factory would have recirculating hydroponic systems. In the plant factory, we didn't assume that you could use the condensed water from the HVAC system, although I think some operations would consider being able to use the condensed water from the HVAC system, which could further improve the water use efficiency in a plant factory. So overall, we found that per kilogram of lettuce produced, it was about 10 times less water in a greenhouse or plant factory than a field. So one of the take-home messages from this work was that CEA in an urban area is not so cost competitive compared to field production. And labor was really the largest input cost for both greenhouse and plant factory. So automation would be a key to bringing down those costs. We also were curious about looking at other location effects. If we could go to a more rural area, it's maybe like Peri-Urban or just outside of that Peri-Urban area where land is even cheaper, but we're still not going that much farther to market. That rural location could give you cheaper land, cheaper energy, cheaper labor, but then greater transportation cost. And so we wanted to look at that component in more detail. This is work that Charles Nicholson, our economist at Cornell, has been working on as a follow-up. This component isn't in press yet. It's not published yet, but it is looking at the effect that automation can have on the cost perspective, as well as moving to a more peri-urban location or even more rural location where land is cheaper. So our field costs stacked up as before. So they were about $3 per kilogram. This is just looking at a New York City scenario. So this second bar would be essentially the same as before. Just note that the colors changed in terms of the colors for supplies, labor, management, packaging, and so on. But again, about more than $8.50 per kilo. So then our third bar is citing that greenhouse outside of the city where land is cheaper. And labor would also be cheaper, at least hourly kind of labor is cheaper in that situation. So notice that our land or structure cost, this blue bar really goes down. And then this red bar for labor goes down somewhat. However, this orange bar for transportation goes up a little bit. So we could reduce the cost to a bit less than $7 per kilo by moving outside of the city. And then the next bar is assuming that we're back in the city, but we're using a more automated system. So we thought of this as like an automated NFT system where seeding, moving the NFT channels around in the greenhouse are automated, as well as automated harvesting. So that brought up the structural cost. So the CapEx, the upfront cost for those automated systems made this blue bar substantially higher. But it did substantially reduce the labor cost, which is part of the OpEx. So economically, if one wanted to look at this more labor efficient system in an urban area, you could bring down the production cost of lettuce to perhaps $6 per kilogram. And then the last bar that we looked at was incorporating both automation in the greenhouse, as well as moving to that peri-urban location where land is cheaper. So you'll notice that the land and structural bar, so the land cost is cheaper. We do incorporate the higher cost of the automation in terms of the structure. And then labor is both cheaper in terms of a dollars per hour perspective, as well as lower labor because of automation. And so we start to see a pathway forward in terms of bringing down the cost of CEA production that both automation can contribute, as well as site selection. And I thought that this was interesting. So in our, I guess this would be an urban greenhouse scenario that was automated. We came up with an input cost of about $6 per kilogram per lettuce. And it was somewhat gratifying to see that matching work coming out of Japan. So the Japan Plant Factory Association has been collecting for several years. They do this survey where they collect data from plant factories operating in Japan. And so they look at electricity, labor, the building structural costs, and then the other input costs were just grouped into one big category. But they were coming out with a total production cost of about $4.50 to $6 per kilogram per lettuce. So we might think of as then Japan is having more mature plant factory production with more automation. That's making that labor cost lower than our initial economic modeling work did for U.S. urban areas. So with that, I want to move on to the nutritional component. So in this National Science Foundation project, we've been looking at the nutrition of leafy greens grown in different ways. We know that leafy greens are an important source of many things, protein, dietary fiber, vitamins, and minerals. There's really not much literature on how the nutrition of something grown in a field can differ from something grown hydroponically in a greenhouse or an indoor farm. In our project, we decided there would be like lots of nutritional components that you can look at. We decided to look at lutein and zeaxanthin, which would be carotenoids. They're eye health pigments. So these are things that when humans consume them, and kale is particularly high in them, they migrate to the macula, to the base of the retina, and they actually reduce degradation from damaging blue light that can get through our eyes. And so when your mother said eat your carrots, and she should have really said eat your kale, she's really talking about these eye health pigments. So in this study, this was led by Marianne Neiman at Rensselaer Polytechnic Institute, and her PhD student, Iosius Ashinafi. And then we assisted them at Cornell. We selected 3 cultivars of kale, Toscano, red boar, and winter boar. These were grown in field, greenhouse, or growth chambers. And then it was quite a detailed study in that we harvested them at 3 different ages, seedling, juvenile, and mature. And then we repeated that over 3 crop cycles as well. And I'll just show a couple graphs. So lutein is one of these eye health pigments. And so we have a couple different graphs. The graph on the left, I need to make sure to advance to the right thing. Sorry, I have split screen, so sometimes I look at the wrong screen. So this is what the kale looked like in those 3 different environments. And then here's the graph of lutein. So we have red boar, Toscano, and winter boar kale. This was at the seedling stage. And then the bars on the right are for juvenile kale. So we have the lutein concentration, and a couple of the main take-home messages are for, at the seedling stage, for all 3 cultivars, we had very similar concentration of lutein in either field or greenhouse grown. But the growth chamber grown, which is our proxy for indoor grown or vertically farm grown, actually had higher lutein concentration. And for juvenile kale, we saw this for red boar and winter boar, that we also had higher lutein concentration in growth chamber grown than field and greenhouse. And then field and growth chamber had similar to each other for Toscano. And carotenoids, which were, this was lutein and zeaxanthin added together. We again saw that similar thing. So I think at least in terms of carotenoids and kale, under our experiment, we had some very nice take-home messages, which are we didn't see any cases where the concentration was lower in growth chamber grown. There was one case, I guess Toscano at juvenile stage was a bit lower in a greenhouse versus a field. But overall, this speaks quite well in that we think we can match the nutritional value, at least for these carotenoids, with urban hydroponically grown leafy greens. Obviously, a lot more work needs to be done with different types of crops under different production settings. But for us, that was initially very positive news. Part of, many of you know our Greenhouse Lighting and Systems Engineering Consortium and the work that we're doing to try to reduce energy use in greenhouses with lighting. We've also been looking at some aspects of this for the National Science Foundation project, which has been looking at the effects of light spectrum on water use efficiency and nutrition. And many of you know that LEDs have really revolutionized the market, and compared to current best high pressure sodium lights, LEDs are now, in some cases, maybe up to twice as efficient. And compared to high pressure sodium lights from 25 years ago, from like a generation ago, even current high pressure sodium lights are more energy efficient than those. And then LEDs have become 2 to 3 times more efficient. Interestingly, LED adoption is, at least in greenhouse environments, or the Department of Energy also tracks this for what they call like single layer sole source lighting, which really refers to cannabis production. LED adoption has dragged behind high pressure sodium adoption. And so those of you familiar with our GLAZE consortium, a lot of the work that we do is to try to understand better all the capabilities that LEDs provide to us, to make it easier for growers to adopt LEDs, and then also try to improve the economics of adoption. In the last, like, say, 4 or 5 years, the return on investment in LEDs has begun to decrease to the point where it's more palatable to growers. So I think we're getting to this inflection point where we're going to see more LED adoption over time. So my grad student working on this NSF project, Jake Hawley, he's been looking at the effects of greenhouse supplemental lighting spectra on lettuce yield, morphology, and nutritional quality. So he's been doing these experiments with several different lighting treatments in the greenhouse, and then we carefully control the amount of light that we supply from treatment to treatment so that it would be the same. So here's some work from Jake from last winter, where he looked at these 10 different spectral treatments. Kind of on the right are what we consider our control, so high pressure sodium and metal halide. And then we had different configurations of white, red, blue, and white, red, and blue LEDs. And overall, we find this, and these were conducted in the wintertime when the sun gives us less than half of the light that we need in a day for optimum lettuce growth. There were not huge differences according to light spectrum on fresh weight. We did see for this cultivar Rex that metal halide fixtures actually gave us higher fresh weight than 90% red, 10% blue LEDs. And then for Ruxai, this red leaf cultivar, there was no significant effect. One of the measurements that we also looked at was the volume. So if you measured the height and the width of lettuce, you can come up with a volume measurement. So under kind of traditional HID lights, so high pressure sodium and metal halide, we did see for Rex, there could be a larger volume, so a bigger plant than an 80-20 red-blue LED. And then for Ruxai, we saw those patterns were quite a bit more accentuated. So there was an even bigger size plant than with metal halide, either HPS or metal halide, than its counterparts with different combinations of red, white, and blue LEDs. So overall, there was not a huge effect on LEDs on plant size. And currently, we have work in progress looking at water use and nutrition. So here's a graph. We haven't, this is work still in progress. This is after 2 crop cycles of work. This is the water use in milliliters of water per head of lettuce per day. And we're starting to see some separation where we see increased water use for ceramic metal halide and high pressure sodium light, and a bit lower water use for the red blue LED or the white LED. We also have in progress looking again at the carotenoids, the eye health pigments, and then mineral nutrients under these different lighting treatments as well. Jake Hawley has also been doing work with carbon dioxide enrichment, and well known is that we can improve crop productivity with using CO2 enrichment. This was a nice example of that, where this is Ruxai lettuce grown for about 3 weeks in chambers with carbon dioxide, if they had supplementation up to 1,600 parts per million CO2, we saw about a 45 to 50% higher fresh weight than control plants that were growing at ambient carbon dioxide concentration. But so far in the literature, there's less work on how carbon dioxide enrichment actually affects the nutritional composition of plants. And so here's what the plants look like. You can tell visibly that there are bigger plants at higher CO2 concentration, which we would expect. Jake has been looking at anthocyanins, so the red pigment, that's an antioxidant. He's been looking at its concentration under the different CO2 treatments, as well as violazanthin, one of those carotenoids that we see in leaf lettuce. And we haven't done the statistical analysis yet, but so far it would appear that there's not going to be a significant correlation between carbon dioxide concentration and either anthocyanins or violazanthin. So in a sense, that would be a good finding in that CO2 enrichment, at least under the context of our experiment, doesn't necessarily reduce the nutritional value, at least of anthocyanin and violazanthin. So then the last component I want to mention, and I'll try to get through quickly so that I can get to the questions that have been coming in, is the work on workforce development. And this has been led by Anu Rangarajan, who leads the Cornell Small Farms program. Originally, she pulled together 12 CEA expert practitioners. This took place before COVID, and brought them together in the same room for 2 days, and they hashed out all the different kind of tasks and duties that they thought a farm operations manager would need. And the facilitated process they used was called DACUM, which stands for Designing a Curriculum. So the idea is, instead of a higher education institution having a top-down approach and saying like, okay, I think CEA workers need to learn this stuff, the idea is to do a bottom-up approach where we go to the industry and we say, what does your day look like? What are the tasks that you really have to know? And then we map that out to a curriculum and think about how we can actually teach those skill sets. And this is available online. If you want to learn more about our NSF project in general, you can go to blogs.cornell.edu and then /urbancea. And that will take you to our broader website. The DACUM chart is posted there. So you can see these 15 different duties that are listed with about 150 tasks. And when I look at this chart, I'm intimidated. I think, how can it be that one person has all of these skill sets? And it could be that at a small operation, there is indeed someone that is doing all of these 150 tasks. In a medium or larger size operation, the idea would be that there would be at least a few different employees that collectively would be doing those tasks. And this work has spawned a new grant that we were able to get from the USDA, which is on accelerating workforce development for the controlled environment agriculture industry. So we just started this project this fall. So we, building off of the DACUM process, we work with industry networks to prioritize CEA training. We work with a couple different two-year institutions, two-year associates programs, one in New York and one in Ohio. And the idea is that there are many different pathways to joining the workforce in CEA. Some of that can be for people already in the CEA industry that want to gain some specific training to build up skill sets. So those could be like online courses or micro-credentials that they take. Others could be students that put together several different courses or micro-credentials and build that up into a two-year associate's degree program. And then that can help them progress in their career. So myself and Anu Rangarajan at Cornell are working on this project. Cherry Kubota at Ohio State And Ohio State has a two-year college that's called the Agricultural Technical Institute. They're located in Worcester, Ohio. We have Uttara Samarakun, who's one of their faculty members. And then the two-year college that we're working with in New York is SUNY Broome, which is about an hour south of me in Binghamton, New York. And we have industry partners with Agriculture, Farm Tech Society, and Glaze. And we're at the stage where we're beginning to propose kind of 3 different tracks for training. So what's involved in training a CEA assistant grower, a CEA head grower, and then eventually a CEA farm operations manager. So far we've been mapping out 6 or 7 different courses that we think would be required for teaching these different tasks at each of these levels. And I think I better end here and take questions. In general, for urban CEA and its pathway forward, a few thoughts that I have are that in terms of being cost competitive with field production, more work needs to be done on controlling costs, such as for labor and energy. If urban CEA is going to be more expensive, but we still want it to be competitive at the marketplace, then we need greater product differentiation. So are there, can we get a higher value for the product if there are real attributes that consumers find enticing, such as it being fresher, nutritious, less food waste, hyper-local? Certainly there's close connections then with workforce development and education. And then food safety in a more controlled environment could also be a benefit. So all of these claims would require a substantiation for a business to really use them or get the most mileage out of them. And then something that I didn't talk a lot about today, but it relates to kind of the broader context of urban agriculture, is that corporate urban CEA could really learn to be more embracing of diversity, equity, and inclusion, which are some of the strengths of more of the community nonprofit urban agriculture that we see in many of our cities around the US. So it'd be interesting to think about how, corporate large scale urban CEA can be more embracing of their communities. Okay, thanks for your attention, and I'll look forward to pulling up these questions that have been coming in.
Thank you so much, Neil. So much information. We do have several questions coming in. So first thing I'd like to say, Neil, do you have about 10 minutes, 15 minutes we can go over the questions?
Oh, yes, I can stay for as long as it takes. Yeah. So if people need to go, they could watch the recording or shoot me an email too.
Yeah, so that'll be my second point. So for all of you who are here, all of you who can stay, we're gonna have 10, 15 minutes for questions. And for all of you who needs to go, it will be available on a recording on the Glaze website later on. So I'm not gonna ask my questions because we have a lot of things to come from the audience. I just would like to make one point here, which is we come here to the end, right? At the beginning, you're talking about the costs and you show how labor is a big effect, and then you show the importance of water and CO2 and lighting, the greenhouse gas emissions. But it's interesting to see how it comes back to the full circle. Now we're talking about the other projects looking into the importance of training labor, and then you talk about the resource use efficiency. You mentioned lighting here most recently. All of these tie together to the initial graphics that you showed at the beginning, the impacts that all those individual parts have into the full life cycle of producing food crops in different conditions. Field, greenhouses, vertical farming. It's very interesting how everything's together. Really complex. There is not an easy answer for that, but very interesting to see how you're connecting all these different points and aspects of the food production in controlled environmental agriculture. So thank you so much for sharing all of that. Let's go to the specific questions. So the first one I got was, is there a place for mass-produced small-scale vertical growth systems that you know of?
Yeah, Mike, I think that's a really interesting question. I think I've been growing on like a small scale hydroponically at home. Last semester, I taught my hydroponics class. About 2/3 of the students were in person and about 1/3 were online. And for those online students, they all had home hydroponic systems, and we grew leafy greens together last fall and did a lot of learning through the process. To me, there were like tremendous benefits that I saw, like having greens grown directly in the home, and both psychological, but also just the like economic value of the food or the nutritional content of the food. And I should theoretically be able to go to the grocery store whenever I want to and buy leafy greens, and I'm blessed to be able to do that. But there were times last fall when my family ate more salads than they otherwise would have because we had fresh leafy greens that we could harvest. So just my own personal experience is I think there are benefits of it. One could be, one could think a little bit skeptically or a little bit critically about, is it going to be the cheapest way to grow food at a small scale at one's home, or one reads now about these like supermarket systems, and it might not be the cheapest, most energy efficient way to grow compared to larger scale systems. But there could be other like these benefits with the psychological value, as well as it may encourage people to eat more healthy fruits and vegetables if they see them kind of actively growing around them. So I think there's definitely more like research work that needs to be done to answer that question, but I think there's interest there for sure.
Thanks, Neil. That question I found very interesting from Kathleen, and I started was she was referring to the slides when you're talking about the labor in different places, and so on in the city. And the comment was that the labor in New York or Chicago had a positive impact on the local economies, while labor in the fields of California might not. So
yeah, and one thing that we hope to do, we still have some more comprehensive life cycle assessment work to do in our study. The economists would tell me that, or like if you look at $1 of income that comes to a farm, that it has this multiplier effect, that you get something like 2.5 times the mileage out of that dollar, because then those local farms, they spend the money they earned in their local community, and that expands the use. So a similar thing should be expected with the workforce as well. So in terms of like building up, or like definitely like there would be that additional economic opportunity, that multiplier effect that you would get with urban CEA. I always think it's funny, then it's like, do we pit states against each other and be like, oh, we don't want economic activity in California, we want economic activity in New York? But I don't think we'll go down that path for today's discussion.
Great. I'll have 2 questions from Will Henker here. I'll pick one in the interest of time. So I'll take the one I think is more interesting, which is how does the quantity of food waste impact economic and greenhouse gas footprint of field industry reference at 4% versus urban local, likely less than 10%. So the impact of food waste, right? We talk about all these.
That's great. Yeah. So in terms of the economic impact, we did try to include that in our model already, where we did assume an industry standard. I forget, it was something on the order of 35-40% waste for the field grown leafy greens, and then we had something like 5% for urban CEA leafy greens. So that was included in our economic analysis. It wasn't really accounted for in our greenhouse gas analysis, or like we didn't look at like the waste could go to a landfill and what happens if it goes to a landfill and turns into methane. And then methane can be an even worse like greenhouse gas than carbon dioxide. So hopefully we'll be getting more back from this broader life cycle assessment that can speak to that part of the question.
Great. Then 2 questions that we can bundle together somehow, which is any theories on why growth chamber environment kale did so well nutritionally? And then another question related to that is what type of light was used in growth chamber maybe that could explain the high nutritional content.
That's great. Yeah. So our colleagues at RPI actually used fluorescent lights for in their growth chamber. And we know that fluorescent lights are high in blue. They also have, depending on the type of fluorescent, a bit of UVA. And so we're hypothesizing that it's actually the blue light that we know that when plants get high blue or UV, that also triggers them to make these compounds, which are light protecting compounds for the plants. So we think that's likely why. Our colleagues at RPI are currently they have LEDs that are capable of delivering UVA and then 3 different wavelengths of blue light, so that they're now looking at how different wavelengths of light are affecting the nutritional composition.
Perfect. Now, the next set of questions, again, I think we can bundle 2 together, is about if you track leaf temperature related to the lettuce trial. So one is asking directly if you track the temperature, and the other one is saying if there is any potential impacts of the leaf temperature when you go with an LED system and HPS system regarding to the lettuce trial.
Yes, those are absolutely valid points, and I think that's a fair bit of what's going on here. Is so we did some spot tracking. We didn't track it with a data logger, but we used an infrared temperature sensor to periodically check leaf surface temperature, and indeed it's about maybe 1.5 degrees Celsius or 3 degrees Fahrenheit warmer under high pressure sodium light than LED. So we do think that is partially explaining the kind of growth benefit that we got from high pressure sodium light. We didn't try to separate the effects of leaf surface temperature from the growth effects. It could be that in a different project, and others have done this, looking at the possible benefits of far red light. So far red light can give you kind of wider, thinner leaves that could help you with photon capture. And HPS fixtures would have some fraction of far red light versus the red blue LEDs or the white LEDs would have quite low levels of far red light.
Perfect. The next question now is about spectrum during the lettuce trials. Did you see different types of artificial lighting or spectrum affect anthocyanin concentrations with the Rothschild lettuce?
That's great. We have a very technical audience today. That's awesome. We did see, we did actually measure anthocyanin concentration. We don't have all the results back, so I didn't show them. Visually, we did see kind of what we expect. So under like blue LEDs, treatments and higher amounts of blue light, we saw greater anthocyanin concentration. So that's a well-known effect. Interestingly, we didn't fully finish the stats analysis yet, but when we took plant tissue samples and ground them up and extracted them for measuring anthocyanins, we didn't necessarily see a statistically significant effect on anthocyanins. And what we think is happening is it's kind of like the outer leaves are where you see the anthocyanin effect. So if we took like kind of a whole plant sample and grind it up, it homogenized the sample. And so some of the greener leaves beneath sort of diluted the anthocyanin effect.
That's a great observation. Yes, that's a great point. The next one is, did you study taste and shelf life? So did you look into that as well? And then the question is that a relevant aspect in the US market? So do the US market care about that?
Those are both great questions. We did not under this project. We've had a couple other projects where we worked with at Cornell. There's in the food science department, there's a consumer sensory evaluation group. And so with a couple other projects, we've looked at the taste of plants grown in different ways. I think that's absolutely would be a really nice extension of the work here is for leafy greens or tomatoes or strawberries grown in CEA versus field. What are their taste and shelf life attributes? Likewise, we also didn't look at shelf life. I would say in the US market, both are important. I think the retailers will value that higher shelf life, or they'll, if it results in less shrink, less product that they have to throw away, there can be a value for the shelf life. I think so far a retailer might not necessarily be valuing the taste, but I think they see if a product sells out quicker, that and the consumers keep buying more of it, that it's sort of at least qualitatively showing them that that taste is important to consumers. But currently they're often not quantifying it for these CEA products.
Sure. Yeah, I know organics, sometimes they barcode every single plant. That might be one way to track that in the future. They have a better handle there. Now, why greenhouse plant factory grown lettuce has higher lutein than the field grown lettuce? Would that be due to the light intensity or spectrum difference, or maybe other factors?
Yes, great question. I think that kind of gets back to the like blue light. So so it wasn't so much that greenhouse had higher lutein in our work. That was pretty similar to field grown, but the indoor plants that were grown under fluorescent lights had higher lutein, and we think that was probably from the blue light from the fluorescent lights.
Perfect. Now, the next one for urban CEA, we have to balance value-added products to compete with conventional non-local food. How do specialty crops fall into urban CEA and hydroponics, accounting for the increased risk and cost? Leafy greens are ideal for these plant factory systems, whereas peppers, strawberries, for example, could be less so.
Oh yeah, that's a great question. So probably so we looked at leafy greens in a sense because there's a lot of market information out there and a lot of status quo information in terms of field production and what all that entails. We also see that like baby leaf greens or hydroponically grown leafy greens are quite common in plant factories currently, or greenhouses, because they are quick turn perishable crops. But I think a different type of analysis would be quite interesting, or what could be like the more like economically important crops to grow. So if they have to command a higher price at market, maybe things like maybe consumers are willing to pay more for really tasty berries, or like differentiated products like microgreens or edible flowers, at least in kind of our early adoption stages of plant factory production. Those might be more like economically important crops than kind of mass market commodity crops, which might be like tomatoes or head lettuce.
Perfect. Neil, I think we have one last question here. It came to the chat, not the Q&A box, which was, I lost here. Just, okay. Did you benchmark the leafy greens with something like carrots? I think they were referring when the question came, we were talking about the eye image, the kale.
Oh, right. Yeah. So, so we did not analyze lutein or carotenoid concentration in carrots, but there would be like USDA kind of average value information from different crops that would be available.
Perfect.
In general, with the kale samples, they're quite a bit higher than what we get for carrots on a per weight basis. But then maybe it's easier for a consumer to eat a large weight of carrots than it is for kale.
Perfect. Well, Neil, that concludes the questions that we had here on the chat today. Thank you so much for staying longer than the booked time. That is excellent, gives the opportunity to answer all these questions. Do you have any final comments for the audience? Any final remarks?
Thanks for sticking with me. You're the ones that made it through to the bitter end. We have about one more year left on this project, so I look forward to talking more about like the more holistic like life cycle assessment. And then we've been doing some great work with modeling energy use in kind of skyscraper farms. So if you think of like a tall, transparent glazed building that has multi-level production. So look for more coming out of our project.
Perfect. Well, thank you so much, Neil. Just make a quick comment for those who stay here to the end. For the next webinar, we're going to be discussing the 2019 Census of Horticultural Specialties. So there'll be a market analysis, just looking for the trends, analyzing the documents, seeing the numbers. I hope you find that interesting and you register for the next webinar coming up next month. Thanks, everyone. Thanks again, you. Have a good afternoon, and I see you, everyone, in the next webinar next month. Have a good day. Bye-bye.
Bye now.